my name is Will Barnes. I'm a postdoc at American University in DC and also at NASA Goddard Space Flight Center. And I'm giving this talk on behalf of myself, as well as my co-authors, Nabil Frage and Jack Ireland, who are both here today, and our other co-author, Stuart Mumford, who I'm sure probably a lot of you, especially on the SciPy side of things, know, but who couldn't be here today, unfortunately. So yeah, I'm going to be talking about ways that we've been able to accelerate the kind of typical workflows that we have in solar physics with SunPy, and also some of the kind of pain points that we've encountered along the way. So first, just want to give a brief primer on what solar physics is. So solar physics is, if you think of sort of traditional astronomy and astrophysics, but about a single star. So solar physics has, a lot of relevance to our life here on Earth. We want to, the more we understand the sun, the better we can understand its impact on the Earth, especially in terms of space weather. So this video I'm showing now is showing a CME eruption, or a coronal mass ejection eruption off the limb of the sun, and it propagating through these different spacecraft that are always observing the sun. And these can have catastrophic impacts on Earth, depending on whether they hit the Earth or not, but really important effects on the Earth. But in addition to the kind of the practical sort of space weather side, the sun also provides this amazing laboratory for studying sort of fundamental plasma physics processes, and as well as details about stellar physics that we might not be able to do with sort of nighttime astronomy, where it's difficult to resolve a lot of these phenomenon. But the primary focus of solar physics is really the atmosphere of the sun, and in particular, this layer called the corona, which is the outermost layer of the sun's atmosphere. And what I'm showing here is a picture that was taken in Australia earlier this year from the eclipse. So this is an eclipse photograph, and during a solar eclipse, you're actually able to see the solar corona with the naked eye, and you see all this amazing structure kind of off the limb of the solar disk. And what's actually really interesting about the corona is that it's when they first started making these eclipse observations, and then later on when they were able to do sort of spectroscopy of these eclipse observations in the early 20th century, what they found was that the coronal plasma was actually many orders of magnitude hotter than the solar surface. And so this is kind of dubbed what's known as the coronal heating problem in solar physics, is this mystery of why, once you move away from the surface of the sun, why does the atmosphere become hotter? It's sort of analogous to if you opened up your oven and you started walking away from it and it suddenly got hotter, right? And a lot of the clues to this problem lie in the magnetic field of the sun. And so what we've kind of discovered over the past sort of 70 or 80 odd years since this effect was first discovered was that the magnetic field of the sun really holds the keys to this puzzle. And it's that magnetic field of the sun, this really complex tangled field that releases energy into the solar plasma. And this is a video from this one particular instrument called the Atmospheric Imaging Assembly that's just looking at the sun all day, every day, in 4K by 4K resolution with a cadence of 12, taking a snapshot every 12 seconds in lots of different wavelengths. As you can see, these really complex structure known as active regions on the surface of the sun. And by looking at these active regions in multiple wavelengths and thereby multiple temperatures, we can start to get a handle on what are the dynamics that are happening on on the sun, and gain insight into how the magnetic field is dumping all this energy into the coronal plasma. So we have all this really rich data, and we want to do science with it. And of course, we're all in this room because we want to use Python to do that science, right? And so the way we do that is through a package called SunPy. So the three of us that are here are some of the maintainers of the SunPy package. And SunPy is our tagline is a community-developed, free and open-source solar data analysis environment for Python. And the idea is that SunPy, provides the sort of core capabilities that you need for doing solar data analysis. This includes the ability to search for and download data from lots of different data providers, load data into kind of data structures that combine, like say, your image data and the associated metadata, so you can do sort of image operations or metadata-aware operations on that. And then there's also our kind of the ability to do coordinate transformations specific to solar physics, and which is really important when we're trying to combine data from multiple spacecraft. I just want to point out that all of this machinery is built on top of SunPy. So SunPy is a really fundamental package for us, particularly the data containers and especially the coordinate stack. So SunPy is a really mature coordinate transformation capabilities, and we're able to sort of glue our solar-specific coordinate transformations on top of that coordinate stack. So SunPy is not just a single package. We have the SunPy project includes the SunPy ecosystem, and so this is really a kind of collection of tools similar to the kind of keynote that we saw this morning. And we have the core package, and we also have sort of additional kind of satellite packages, if you will, for doing more specific tasks or looking at more specific data from specific instruments. But they all kind of share this kind of common underlying core capabilities provided by SunPy as well as SunPy. So I just want to give a few quick code snippets that kind of show how this kind of data analysis workflow works in SunPy. So we have capabilities for doing, like I said, search of data. So we have this particular object we call Fido for searching and downloading data. So Fido searches and fetches. And you can search using sort of time attributes and wavelength and searching for specific instruments. And so I'm searching for a particular active region, the one I showed earlier, and then you get back these nice kind of rich tables of metadata. And then after you do that search, then you're able to download those files as FITS files locally to your machine, and you're ready to do your And after that, you can load these files into your data structures, to do your analysis on. So we have this data structure called map, which essentially is a container for holding the image array plus lots of associated metadata, and for doing kind of quick visualizations like the one I'm showing here. So this is a full disk image from AIA at a particular snapshot in time for one wavelength. Now that we have those data in our kind of nicely packaged data containers with our underlying metadata, we can inspect each of these operations and pull things out like the certain properties of that observation. Things like what detector made that observation, what wavelength was it made at, when was it taken, and where was the satellite taken at. And I just want to point out that all of these metadata attributes on these objects are returning sort of core data structures provided by SunPy. So for example, an SunPy quantity, which is just a number or an array plus units, or an SunPy time object, or an SunPy coordinate object, which is a place, a location plus the coordinate frame that it's located in. So using these data containers and all these really nice rich objects, we can do things like crop an image, by expressing where the bounding box of that image is in our kind of physical coordinate system, rather than trying to do this in our pixel coordinate system, for example. And that we can also do transformations between these more kind of intuitive world coordinates and the pixel coordinates in our image, which allows us to sort of extract the data from those underlying arrays. So these map data structures and these fundamental data structures provided by SunPy are really key to a lot of our kind of exploratory analysis with Python and with SunPy. Additionally, we often want to align data. So when we're looking at these this amazing movies and trying to understand the dynamics of the field and the plasma in the atmosphere of the sun, we often want to look at multiple sequences of images in time. This is made difficult by the fact that the sun annoyingly rotates from the point of view of Earth. And so if I take an image of the sun and I crop a particular region, and then I look at the sun 12 hours later from that same viewpoint, and I crop the same region, that bundle of plasma that I'm looking at has rotated. Luckily we have a good idea of what that rotational rate looks like. And so what we can do is that we can use the sort of machinery provided by again SciPy, and as well as some additional solar specific machinery we put on top of that to account for this. And in particular, we can use, so this line, this is actually all the code that generates these figures here. So it's just to drive home this point, this is made relatively easy by these tools, is that we can reproject just using some given coordinate system. We can use the fact that our map object is aware of the coordinate system that it's in to reproject that image to some given cutout frame, and that's the one that I showed earlier. And what this allows us to do is then get back a sequence of cutouts that are both shaped the same and that are looking at the same piece of plasma and are tracking that active region as it crosses the disk. And then that allows us to then stack all these images up and do our analysis in time, on lots of different areas within this really magnetically complex region. All right, but so this whole workflow that I've showed is mostly done on a laptop or a big desktop. But it turns out that the data volumes that we have make doing this on a single machine really challenging. And in particular, analyzing many time steps of solar image data requires many different files. Typically, the way these files are delivered by data providers is that you get one file per time step per wavelength, which means if you're trying to look at 12 hours of data at a 12-second cadence for 6 different wavelengths, to get the temperature coverage you need, you're looking at nearly 22,000 individual files. For anyone who's tried to deal with kind of large file sizes, especially downloading those, knows this is a problem. As I've showed you, working with these map objects is really great and provides us a lot of really nice metadata aware computation that we can do. But instantiating these for many files is difficult, especially when you're trying to do this in RAM. When you have something like 130 megabytes per file for the same data set, 22,000 file data set, you're looking at something that doesn't even fit on your laptop, let alone in RAM. So like I said, all of this processing requires you to stack these images into these data cubes. And this places a kind of a large computing burden on the user. But the problem with a retort might be, okay, why don't you just why isn't the data provider just building these data cubes for you and delivering them to users? Well, the fact again that the sun is rotating and that these active regions are popping up on the sun all the time, especially during a time like right now where we're approaching solar maximum and the sun is really active. That there are many active regions on the disk, and it's just not possible to produce sort of these analysis-ready data cubes for every single region any scientist might want to look at. And so there's sort of this trade-off between, I want to, get my hands in the data and really explore something, but then also I have this need to, unfortunately, batch process and then shove to disk and then do this sort of analysis where I build up this data set before I actually do my exploratory stuff. And this kind of impedes the scientific process of trying to look at data quickly and look at different portions of your data quickly. So fortunately, one of the solutions to this has been this thing called HelioCloud, and this is a NASA-funded data analysis environment for heliophysics that's hosted on AWS. So this is very in line with this NASA movement to transform to open science, or TOPS initiative that some people might be aware of. HelioCloud is essentially a Jupyter Lab interface running on AWS with a bunch of data, just like the ones I've been showing, right next to it, which means this, we've eliminated this need to download, these 22,000 files to your computer. They're now just sitting right next to your Jupyter notebook, and it means that you can use tools like Dask, plus, the tools that we're used to using, or that astronomers and solar physicists are used to using, like SunPy and SciPy, to do this analysis. Okay, so now I'm going to switch to the riskier part of this presentation, which is a live demo of everything I just showed you, but at scale on HelioCloud. And we'll see how this works given the difficulties I was having earlier. Okay, so Let's see. Oh no, my cluster is not there. This isn't good. I tried to cheat and start the cluster up beforehand, but it does not appear that has worked. So what I'm doing here is I'm just, for the people in the audience who are kind of, have used Dask before, I'm setting up, oh no. All right, well this might not work. All right, we'll try one more thing. When in doubt, just restart the kernel completely, right? What could go wrong? It's all right. There's a rendered version of this, so at the very least, we can see what the end result is. But it's more fun to watch that work actually be done, right? Okay. This did work at some point, I swear. So what I'm doing right now is I'm setting up a Dask cluster. Okay, let's see. Okay, now it's giving me, okay. Now let's shove this into our nice little, and of course it's not going to work right now. All right, well that's okay. We'll just try to do it in the other. And I'm setting this up through something called Dask Gateway, which for people who haven't used this before, it's basically a way for like system administrators to have like sort of a single unified interface to setting up for users to set up a Dask cluster, but then where a single kind of party can control how that Dask cluster is provisioned. So what I'm going to do is I'm going to, as before, search for data like I showed, but instead what I'm getting back, instead of a list of files that are on some remote server that I have to download, I'm getting a list of S3 URLs that are just on a bucket that I can access directly from Jupyter Lab. So next, what I'm going to do is I'm going to identify this sort of same region, the same active region that we're interested in studying. So, but what we want to do is we want to look at this same active region again, but for a period of 12 hours. And so what you can see here is when I do this, when I get back this list of S3 URLs, I'm actually getting back only about 180 of these, and that's because these are at a 4-minute cadence instead of this higher 12-second cadence that I mentioned before. But this will still sort of illustrate this point. And so what you can see now I have just, this is just sort of a typical analysis. I have everything is in just in RAM right now. And so what I'm going to do is just create this cutout. And so this is the region that we want to track across our 12-hour period. All right, so then this is the more exciting bit. So now we're ready to load all of these the maps for every single time step for our 12-hour interval that we want to look at. So the first thing we do is we're going to go grab all the headers from all of these FITS files, and what that contains, as these are basically just a bunch of dictionaries. So this is not the image data. These are all I can pull 10,000 of these into my notebook, and it's the memory footprint is manageable. And then what I'm going to do is I'm going to read each of these the data from each one of these files into an array, but I'm going to express this as a Dask delayed operation. And what that means is that I can create a map from each one of these FITS files where the header is in memory, so I can create the map using the header and the metadata, but then the array data is a Dask array. And so what happens then if I give you this preview of my map, where before I was getting this full disk preview, now it's just showing me my typical HTML representation of my Dask array that's in the memory of the cluster, or will be added to my task graph once I'm done sort of building it up, but it's not in the memory of my notebook, and that's going to be and I have 180 of these things, right? So now I'm just going to go through my typical steps of my analysis. So these are things like what we call exposure time normalization. So on these telescopes, typically the shutter on them is open for some amount of time for the light to come in. And that might be variable per exposure and might vary from one instrument to the next. And what we want to do is normalize that out. But again, this is just simple the data array divided by some scalar value. And what that means is that once we do that operation, we still get a Dask array back, that we still have this map that's lazily loaded and lazily executed, but that we have this combination of this lazily executed Dask array plus our still metadata-aware object. Thanks. So this last bit is the kind of the more exciting. So now we want to do this sort of reprojection step where we align each image to this kind of same pixel grid so we can build up this data cube. And so what, again, I'm doing is I'm expressing this reprojection step as a Dask delayed operation. And so what now you can see is that I've cut down this array to a much smaller field of view, and one that is where every single time step is aligned. And I can then look at, if I go and then look at the first one, you can see if I flip back to my Dask cluster, it is doing something to pull that one single time step into memory and give me a nice view where even though this particular one is offset by 6 hours from the field of view that I was looking at, it's been aligned because I applied this operation to each one of these time slices. Okay, so the last step is just to take all of these and stack them into this object called an ND cube, which I won't really go into, but ND cube is a SunPy affiliated package that provides X-array-like capabilities, but with the caveat that it uses something called a WCS, or a world coordinate system, to express these coordinate transformations between your pixel coordinates and your physical coordinates. But basically what it is a metadata-aware stack of all of these images that I have. And this is what this Q171 is. And when I look at it, I can see that I have, again, this nice Dask HTML preview, and you can see all of my chunk sizes here as well. And I'm actually going to skip all these steps because I'm running a little low on time. But here, all I've done is combined all of these steps into one single function, and I've done this exact same step, but for a different wavelength. And so what this gives me is plasma now that is at a slightly different temperature than my first wavelength. And the kind of last step that we would want to do, and this is just the sort of science result part, something that you would actually put in a paper, is that we want to do a cross-correlation analysis between these two wavelengths. And what that tells us is how the plasma is cooling between those two temperatures. And by doing that, we can then make a map of that resulting, those resulting cooling times. And that then tells us something about how the plasma is evolving across this entire region. So I'm just going to, I've then built up this, I have this Dask array, but again, this is something that's still not, it's still been lazily computed. But when I go to actually plot this thing, this should kick off, all of these operations in my Dask cluster, and it has. Oh, okay, good. We'll see if this cluster scales up so this can actually finish in 2 minutes. So what this is doing, again, is it's taking every single one of my level 1 images, it's normalizing by the exposure time, it's cropping them and reprojecting them to the right field of view, stacking them, and then performing this cross-correlation analysis. And to just give you some perspective about what this looks like compared to the sort of normal solar physics workflows, what people will typically do is that they'll spend a day downloading the data for one sort of active region. They'll then spend the next day doing these kind of cutout things, maybe like 2 or 3 days. They'll produce a data set, they'll stick it on disk, and then they'll spend the next 2 days doing this cross-correlation analysis pixel by pixel, maybe on their laptop, say. And so what we've been able to do with this platform plus all this data is reduce that whole week-long pipeline to a single notebook, right? And that we can do this sort of end-to-end workflow with these kind of checkpoint steps along the way. So while that's finishing, I will just show my last slide, which is just basically the summary. So there are still some kind of pain points here. So pulling these map objects, creating these map objects backed by Dask arrays is still awkward compared to how we usually create these maps from FITS files. Typically, you just stick a file name in, and you get back this great map object. As I showed you, you have to do some kind of, writing the loading function as a Dask delayed, method, which isn't, especially painful, but for someone who may not be familiar with Dask or trying to convince them to move this workflow might be a difficult sell. Some of these map methods, for example, the reproject option, still require, eager execution. And so, in other words, even if I put in a Dask array, I might still get a NumPy array out, and the computation might happen instantly because it's not implemented as sort of a lazily aware operation. There's still this incompatibility between Xarray and WCS. You might ask, why are we not using Xarray for any of this? And there are reasons that I won't get into right now because I don't have time, but there is ongoing work to kind of bridge that gap and to bring these two technologies together, because we would love, on the Astro side, would love to be able to use Xarray for a lot of these things. And there's also, unfortunately, some kind of friction between these rich AstroPy quantity unitful objects and the sort of Dask ecosystem that also there's kind of active work being done on. And it looks like this thing is actually finished. So this is the resulting thing that you would actually go and stick in your science paper. And so what you're seeing is like these red colors are indicating that you're first seeing plasma in this hotter channel, the one thing I called 193, and then in the cooler channel. And this cooling is organized, along these loop structures because the plasma is confined to flow and it's heated and cooled along these loop structures. And so what we're now able to do, with this combination of, the kind of solar physics Python stack, things like Dask from the kind of wider scientific Python community, and now this platform, is we can do this end-to-end analysis, without the latency of having to bring the data to our computers. So I will just end with my summary slide, and I'm sorry I went over. So thanks very much.
All right, we're going to take some questions.
Hi, I work on the DKIS project with Stuart, so we are very, very grateful
Yes.
to SunPy and Fido and all of that to manage our data. I wish you were around when I was doing my grad school thesis on chromospheric condensation. Would have been way easier. But do you guys have any tooling, or do you have any plans to implement tooling using HelioCloud to do some sort of quick look before someone has to download data, so they don't have to, grab all that, not necessarily download it.
Yeah, so I mean, if you're looking to just like quick look a single like fits file, that is super easy to do because all the data is there just in the bucket. So you could just pull that straight into like a SunPy map object, or load it with AstroPy fits, for example. It depends on, I guess, if you're talking, of course, in the case of DKIS, where you have these really large data cubes, that's maybe a bit more difficult. But
Okay.
I would say it depends on how the data is laid out and how it's shaped. Yeah.
Thank you.
Yeah, great presentation. Thank you. Just a question about the data access part. Was that part of the process to deploy HelioCloud to migrate the data sources to the cloud environment? And does that involve changes in the API, or how does that?
So this is a kind of a NASA initiative to move a lot of this data that's typically kind of been provided by more traditional data providers through like FTP servers or other sort of systems, to moving it to the cloud to enable this type of science. I think the thing that we're still working on is figuring out ways for our code that's more used to loading these local files and getting it to work with, for example, like S3 URLs. And there's not huge pain points, but there are sort of small frictions that we still are looking to deal with. Yeah.
All right, we'll do one more question.
Yeah, thanks a lot for the talks. So just one question from my side. What were the main reasons of choosing Dask? I guess there are probably like many alternative solutions to that. And the question is, did the SunPy community put in the work, for example, of evaluating different systems for their use case, and then like making, let's say, like an informed decision on this?
Yeah. I guess my sort of personal opinion is that Dask allows you to move from sort of a more local computing environment to a scalable computing environment with the least amount of friction compared to any other option I've seen. Especially something like the Dask array interface. That everything sort of everything like a NumPy array and a Dask array are indistinguishable in a lot of contexts, right? And especially from a user perspective. But I think what we've our impression is that, Dask is the solution for parallel and distributed computing that, is the most popular in this community, in the scientific Python community. It's not that we're necessarily closed off to other options, but it seems like the one that has the most support, especially in the context of tools like Xarray or the visualization tooling that surrounds that as well. Yeah.
Okay, thanks a lot. Yeah, I
Yeah.
guess we have with our project like similar decisions to make in future. So I'd be happy to talk to you offline.
Sure. Yeah. Definitely.